Yeah, so this is joint work with Irit and Siqi. Siqi's here in the audience, so if you have any questions, you should ask her, not me. Okay, so let's start with what a code is. So we're going to be interested in like linear codes. That's also usually what people encoding theory study. So a linear code is simply a linear subspace. Oh, is there a mic? Okay. Okay. Hello. Wow, it's much louder. Okay. Yeah, so linear code is just a linear subspace. And the two parameters people are usually interested in are rate and distance. So rate is like the size, it asks what the size of the code is. So it's going to be the dimension of the code over n. It's going to be a number between 0 and 1. Bigger the rate, the better. We're going to shoot for just a positive constant. Relative distance is like how far apart different code words are in Hamming distance. So it's a minimum of the Hamming distances between code words over all possible pairs of code words over n. So again, this is a number between 0 and 1. And sort of the bigger, the better. You're also going to aim for a positive constant. So I guess like error correcting codes maybe originally started from this like communication problem where Alice is trying to communicate some message to Bob over a noisy channel. So because it's noisy, she can't just send her message in the clear because then an error happens and Bob doesn't know what she's saying. But instead, the solution is to send an error correcting encoding of her message. This way, even if a few errors occur, Bob can still round to the nearest code word. Like there's a unique closest code word that he can kind of correct to. Okay, anyway, that's an error correction. That's like the communication problem. Let's forget about that. Let's talk about some homomorphisms. So sometimes you're going to want some additional properties of codes. So two properties you might want. The first one's addition. This one comes for free for linear codes. So the property of addition just asks that for any a and b in your code, the value a plus b should also be in your code. So this is just like this is true for any linear code, so that's good. The harder property to get is what's called multiplication. So this asks for any a and b in your code, you want the resulting code word or the resulting word if you take like a coordinate-wise product of the two code words to also lie maybe not in the same code but like a related code. So this is sort of like component-wise multiplication operation. Yeah. Okay, and so like what are the applications? Well, really like what addition and multiplication let you do is they let you do some sort of like homomorphic, I don't know if you guys do any crypto, but some homomorphic computation on the encoding. So like you can take two code words and you can perform this addition or multiplication operations without ever having to decode. So this has lots of applications for like computation problems, like secret sharing, just like secure computation in general, PCPs, etc. Maybe let me just quickly just show you what secret sharing is, just so, I don't know, you can see why multiplication is so nice. So in secret sharing, the way it works is you have a share S, and you're trying to kind of like distribute some, or sorry, you have a secret S, and you're trying to distribute shares of it to different people. So that none of them really know anything about S, but together they have enough information to know what S is. So what you do is you take S and some randomness, and you encode it using your good error correcting code. And then you can split up the encoding into many different parts. These are called the shares. You give one to each person. So now everyone has a share of the code word. Because of the randomness you injected and because of the distance, none of them individually know anything about us. But okay, so now let's see what happens if we have two different encodings or two different secret sharing schemes of two different secrets, S1 and S2. So now like, each party has just like one share of the encoding. What they can do, like let's say if everyone has one share, if you just component-wide multiply, you take your two shares, you don't know anything about S1 and S2, and you multiply them, right? You end up with a share of like S1 and S2. Here you just think of maybe S1, S2 as like binary strings, so 0, 1 strings. So when you multiply them, really like these are all everyone can locally compute it. And here you get just like S1 and S2 component-wise also, right? So that's really nice. Like, yeah. Some randomness, yeah. That's randomness only there for like privacy reasons. Yeah. Yeah. So basically, like everyone, like without even knowing what S1, S2 is, can like kind of compute on what S1 times S2 is without having to decode. Okay, so that's like why multiplication is so useful. Also, addition, also the same recipe holds. Yeah, and like the really nice thing about having addition and multiplication is if you have these two things and maybe also like a not, which is really just a subtraction, which is also addition, you can do like universal computation. So this really lets you do kind of universal computations on code words. Okay. So what are some examples of multiplication codes? So I think like all the codes we know with multiplication really are some sort of like function or polynomial-based codes. So Reed-Solomon, Reed-Muller are both polynomial-based codes. There's these algebraic geometry codes which go to like rational functions, and generally these evaluation codes. Let me just tell you what the Reed-Solomon code is. So in a Reed-Solomon code, you will pick n different evaluation points, alpha 1 up to alpha n, in some field of your choice. Okay, so fix these evaluation points. And now your Reed-Solomon code is going to consist of a bunch of code words. Each code word is going to correspond to some polynomial of degree less than k. So k is like some like dimension parameter less than n, so you can kind of choose it to determine how big your code is. So you take every polynomial of degree less than k, and you write down the evaluations f of alpha 1 up to f of alpha n. That's why it's called an evaluation code. Yeah, and then, so this is your code words, or these are your set of code words. And now let's say we have two code words based on the polynomials f and the polynomial g. And let's just check that it has a multiplication property. So if you component-wise multiply everything, what do you get? Well, you get f times g evaluated on each evaluation point, right? So this way, like, if you have two polynomials, you get a new polynomial. Yeah. Okay, so we talked about secret sharing. Let's talk about PCPs. So why are PCPs related to codes? Well, there's like a sort of a philosophical relation, which is that codes robustly encode information, right? PCPs robustly encode computation. So there's some sort of like, I don't know, maybe just, yeah, some high level relations there. But not all codes are going to be useful for constructing PCPs, right? So like some codes are going to be more useful than others. What is this property that you need to create PCPs from codes? Well, let's think about what a PCP is, right? Like a PCP is like some like proof of computation, right? And it has this nice extra property that a verifier can query just a few locations of your proof string and check the computation that way. And so similarly, like if you try to maybe go back to the codes regime, there's this notion, like a coding theory analog of a PCP, which is called a locally testable code. So what is a locally testable code? The locally testable code is one in which you can test distance to the code space. So instead of checking computation, you can test distance by looking at just a few locations in the code word itself. So just like schematically, this is a code word. So if you want to test distance to the code space, you can query just maybe constantly number of locations. And if your word is in your code space, you should accept. And if it's far away from the code space, you should reject with pretty high probability, right? So the way I've written it here is that if your word is not in your code space, then you should reject with probability kind of growing with the distance. Why this? Like, why can't we just always reject like if the word is not in your code space? Well, it's because like if you have a valid code word and you change one bit and you query just a few locations, you're not very likely to hit that bit that you changed, right? So like it's only when the distance is growing that you can start detecting more errors if you query only a few bits. But okay, so that's the definition of a locally testable code. Yeah, okay, and so in general, like I think like sort of historically, if we had a locally testable code, we also knew kind of a PCP construction from it. So this is kind of like so there's no formal relation between the two. I don't think it's known how to go from one to the other. But it was like historically just like, if you had a Reed-Muller code, you could also do like a PCP from the Reed-Muller code and so on. This all changed a few years ago with the construction of these nice C3 locally testable codes, OTCs, which had better parameters than known for PCPs. So these are codes with constant rate, constant relative distance, and locality. Locality is like the number of bits you have to query to test your code word. And like, okay, this is a beautiful construction, but like, why couldn't we use it for PCPs? And the answer is really that like it's a really nice like combinatorial construction, but it's lacking a lot of like the extra kind of properties you need to make the code compatible with computation itself. So in particular, it's lacking the multiplication property. So maybe the main question for today's talk is, can you construct a C3 OTC, a C3 code with a multiplication property? So besides PCPs, this is also an interesting problem in the quantum world. So in the quantum world, there's this like big open question right now about can you construct these good quantum low density parity check codes with something called a universal with a transversal T gate. A transversal T gate is this like gate that lets you go from kind of Clifford operations, which you should think of like addition, to like universal computation. So really like the multiplication as like of the quantum world. And so yeah, so I think it's really interesting because like somehow this multiplication property, it turns out, will actually give you these transversal T gates. So there is like somehow the same like classical property that lets you go from like just linear computation to universal computation also lets you go from like Clifford to universal computation in the quantum world. Yeah, and this problem here is actually maybe an easier version of the quantum problem in the sense that like it's only a one-sided version of these good quantum LDPC codes. I won't really say what that means, but yeah. But yeah, I think like if you can make progress on this question, probably it will lead to something here too, which I think would be really nice. So anyway, we don't solve this question, so but I think it's a really good question, so you guys should try to solve it. But what we do is we construct a new family of codes with some nice properties. Okay, so yeah, so here's our theorem. So for every parameters p and k, p is going to be some prime, k is some constant less than p. So these are both constants. You can define some family of codes. And depending on how you pick k relative to p, there's going to be kind of two settings for like what the properties of the code we were able to show were. So if k is small, so in particular if k is like less than p over 4, we were able to show that the code family is locally testable, and it has a multiplication property. But we don't know if it has good rate, which is one thing. Sad. If you guys, it probably has better rate than what we know to prove, but we don't know how to show better rate. And if k is large, then the code has good rate and distance, but we don't know if it's locally testable, and it certainly does not have the multiplication property anymore. So that's what we were able to show. So maybe let me just tell you what our code looks like. Yeah, so I had this whole like introduction thing about like expander codes, but I was timing it last night. I didn't have any time, so I'm just going to kind of jump into it. Hope that's okay. Yeah, so the starting point is like this coset complex of Coffin and Oppenheim. Okay, so I feel like whenever I see like coset or like complex, it sounds really scary. So let me just like say what a like complex is. A complex is just a set of vertices, edges, and triangles. Okay, that's in your head. That's what it is. It's a hypergraph. Okay, it has vertices. It has a bunch of edges, which are two hypergraphs, right? And like, or two hyper edges, and then triangles, which are three hyper edges. And these like vertices, edges, and triangles. So it's like a generalization of a graph. And it's like these edges and triangles have some nice properties where they overlay in some nice way. I won't really talk about exactly how that works, but yeah, so really this is what a complex is. And then the coset part comes by how you define the edges and the triangles. So let me just tell you kind of how these coset complexes work. So yeah, so you have these subgroups. Let's say you fix subgroup gamma. Fix subgroups H1, H2, and H3. Okay. And now the way we're going to define the vertices, edges, and triangles is as follows. So vertices are going to, so everything's going to be cosets of subgroups. That's why it's called a coset complex. Vertices are simply going to be cosets of your subgroups H1, H2, or H3, right? And then the question then is like, when do two vertices share an edge? And let's say they share an edge when they have some non-trivial overlap, when the two cosets have some overlap. So if you look at two groups, let's say there's a common overlap of G, you can intersect them to get this coset of this subgroup, right? H1 intersect H2. And similarly for the other ones. So the edges also are going to be cosets of some like intersection groups. Okay. And now like, okay, let's get triangles. When do three vertices share a triangle? Let's say that they're all contained in the same triangle if they share the same point. Okay, so there's some G in all three of these, where their intersection is going to be that thing up there, right? It's G times the intersection of H1, H2, and H3. Yeah, and like also if you look at like sort of edges, like two edges, when do two edges lie in the same, when do two edges lie in the same triangle, it's really when they also share some element, right? So you can intersect them that way too. So I think all this kind of makes sense in terms of, yeah, just like things are share connections if they share some element in the coset. Okay. So the coset complex we are going to use is going to be based on some matrix groups. Our coset complex is actually not the one presented in KO, although it's very similar in some sense. Like it's really it's basically the same thing, but it's like a slight variant. Let me tell you what it is. So we're gonna pick the group gamma to be this SL3. So these are 3x3 matrices, determinant 1. And they're like the coefficient, like the entries in the matrix are going to be polynomials in T up to degree M over a field FP. And then so what are H1, H2, and H3? The 3 subgroups are going to be like sort of sets of matrices that look like this. I don't know if you guys can see this. So it's like matrices with like ones on the diagonal, and then there's like this like linear term right above the diagonal, and then some quadratic term above that. It turns out the set of such matrices forms a subgroup, so this closed under multiplication. And like it doesn't really matter which, that we chose this upper triangular thing. We could have also chosen like this. I mean, if you rotate it, it'd be upper triangular, but this like kind of triangular thing, or like this one too. So you take these 3. These are your subgroups H1, H2, and H3. So your vertices are going to be all the cosets of these subgroups. Okay. When you go up a level, you intersect GH1 and GH2. Notice that like the intersection of like this subgroup and like this subgroup, well, it's just this linear term here. This is like a T term here. That makes sense. Like these two up here are both zeros here, so this can't be an intersection. And like these two are both zeros over here, so they can't be an intersection. So the intersection is really this like subgroup here. It looks like this. There's an AT, just like a single linear term above the diagonal. And similarly for the other ones. And then finally, when you intersect like all 3 of them, if you look at all 3 of these matrices, like the only intersection of them all is an identity matrix. There's not really any like not off diagonal term that is non-zero in all 3 of them. So really like the top is going to be like cosets of like the subgroup, like the identity subgroup, the trivial subgroup. So just elements G of your SL3. All right, so that's like kind of the complex we're going to use. Okay, let's forget about that now for one slide. Let me tell you what the code is. So now let's just like go back to the simplest overview. We have a bunch of vertices, edges, and triangles, and we have some nice properties of this simplex, which is that every edge will have like many triangles surrounding it. Okay, so like that edge right there, many triangles around it. Similarly, it's not true just for like that edge. It's true for like any edge in the complex. So like if you look at like this one, right, it will also have many triangles around it. I didn't draw more because it gets very busy very fast, but that's kind of what this complex will look like. So anyway, so let's say we have this D-regular coset complex. D-regular just means like, let's say the number of triangles around each edge. What we're going to do is we're going to put code bits on triangles. So that's where your bits of your code will lie. So the code you get, the block length, like the number of bits in it, will be equal to the number of triangles in your complex. Okay, so then after you define like where the bits lie, you have to say what the constraints are. So you define the parity check matrix. So the constraints are going to be put at edges. So what this means is for every edge, you'll see some number of triangles around it. You look at those triangles, and you say, and the edge tells you that the triangles around it needs to belong to some base code. So this base code would kind of place constraints. So say like it has to be among this list of possible words. It can't be anything else. Okay, so that just fully defines the code. Actually, sorry, I need to tell you what the base code is. We're going to take Reed-Solomon. Why Reed-Solomon? Well, we wanted the multiplication property, right? Reed-Solomon is good for multiplication. And if you think about it, like, let's say every single edge tells you that the surrounding triangles has to be Reed-Solomon. Once you take 2 such simplicial complexes and with a code bits on each side, and you multiply them, you look at a single edge, you look at the triangles around it. If the 2 original words are both Reed-Solomon, and you multiply them, you get a new Reed-Solomon code, right? So this complex will have the multiplication property just from like how you define the local codes. Okay. And okay, so this defines a complex, but if you want to show locally testable, it turns out that you actually need to somehow so like connect or like say how the different edge checks are related to each other. So turns out the way to do this is to assign like meta checks at vertices. So what this means is like if you look at every vertex, there's a bunch of edges coming out of it, right? There's a bunch of triangles, first of all, coming out of it. These triangles are related by edges in different directions. And so if you take all these triangles and all these edge checks around the same vertex, so it tells you like what like the view of each vertex has to look like. And so in particular, it will tell you that the triangles touching each vertex should belong to some, we'll call it twisted code, which is some like kind of twisted product of your two resolving codes. Okay. Yeah, and so if you want to show locally testable of the global complex, it turns out you need to show some like local testability of the local code. The way the proof would then show global local testability is you do some sort of propagation argument, like it's saying, oh, my local code has this nice property, then because of expansion, you can sort of get more. Yeah, so and then we do prove this agreement testability for the local code when your parameter k, this is like the degree parameter for the Reed-Solomon code, is small enough relative to p. Okay. Okay, that was a bit fast, but hopefully that kind of made sense. I guess the last thing I wanted to just tell you is rate and distance. So distance is pretty easy. It again follows from expansion of your complex. The idea is like if you have, it's suffices to look at like a distance from like the 0 code word to any non-zero code word. So you want to count the minimum number of ones in any code word. And the way the distance argument usually goes is like you have some ones in your complex. So then around, because the distance has a local code, there has to be a bunch of ones around each vertex. And then each of those neighbors has to have many ones around it. So as you keep going, you get more and more like non-zero bits in the complex. So you get distance from expansion. For rate, the kind of like one of the only techniques we have for counting rate is what's called constraint counting. So this is, you literally look at the number of triangles in your complex, and then you subtract off like the number of like constraints placed by each edge. And if you do it, you'll see that the rate is going to be this quantity here, 3. This is a rate of the local code, 3 R naught minus 2. But if you want the local code to have the multiplication property, you actually need the rate to be less than 1/2. Right? So if you plug in 1/2 into that, you get a negative number. That's not very good. So yeah, so constraint counting alone won't give us anything in this low rate regime where multiplication will work. So we will argue non-zero rate. This is why we can't argue good rate. We only argue like some small polynomial rate by showing that our code actually contains some like some other family of codes. And what is that code? Okay, actually, yeah, I guess I didn't write it immediately, but the code we're going to show embeds into it is a Reed-Muller code. And the way we do this is literally we just show that our complex actually has a nice embedding into some Cartesian space. If you can show some nice embedding in Cartesian space, then all the polynomials that you get from the Reed-Muller code will give you code words in our code as well. So the embedding is really as follows. Like if you look at a triangle, it's just a matrix, a 3x3 matrix. And it's a 3x3 matrix with these like polynomials inside each of the entries. Each polynomial has degree less than m. So you have so basically what you can do is you can write all the coefficients of all your polynomials. There's 9m of them, and that would just give you a point in fp to the 9m. And then if you look at edges, this is just like some matrix times there's like a AT term here. It's like a linear sort of space. So there'll be lines in FP. So you're basically what's happening is like actually like we have, okay, yeah, let me just keep going. Okay, and then the vertices are going to be these 3D spaces in the Cartesian space. Okay, actually, let me not say anymore. Let me just say that this complex, so it embeds likely into the Cartesian space, so we can show Reed-Muller is contained with our code. Okay, that's it. Cool. So summary. So our code, I don't know, it's a family of codes. I think it's pretty nice. The complex is really beautiful. So, I don't know, it can't be that bad. But we weren't able to show too much, but what we were able to show is when k is less than p/4, we showed it's locally testable and it has a multiplication property. Leaving rate as an open question. It'd be really nice if you can show like ideally, constant rate. And when k is bigger than 2p/3, the constraint counting will work. So you can get good rate, but we don't know multiplication and we don't know local testability. Okay, and then the final questions I just want to leave you with are the two I said earlier. So can you construct the C3 code with multiplication? And also like the quantum question, can you construct quantum LDPC codes with the transfer T gates? Yeah. Okay, that's all.